Okay, so this broadcast, this Google Hangout has started. This is for the Chemistry Unit 5 test, which we're having on, I guess today is Tuesday, Wednesday, Thursday of this week. So if you guys will click on the question and answer app, and then you can ask questions about anything. I imagine some of your questions would be related to the study guide or the worksheets. So just type those in and I'll answer them as they go in. I felt like in the meantime, I could start with looking at the essential skills and then go from there. So what I'm going to do is I'm going to open up some of the documents from Schoology that are in the folder, the Unit 5 folder. And if you look at your assignment sheet, that has the essential skills on it. So I'm going to share that document with you so you can see it. There we go. And I'm going to make it a little bit bigger. I think it gets hard to see otherwise. Okay. So we have 4 essential skills. The first one is know the difference in strength of intermolecular forces between solids, liquids, and gases. 2 is biological molecules form mainly covalent bonds. 3, students know the backbone biological molecules are mainly carbon-based because it forms 4 bonds. And students know how intermolecular forces affect boiling point. And that 4th one is what we just did in the most recent class. So I'm just gonna start with the first one. And actually the first 3 are really easy. I have not looked at all the quizzes yet, but my understanding is that students did pretty well on those. So I'm gonna share, I have bamboo paper. And there it is. So I'm going to start and go from there. And then as questions roll in, I can start answering those questions. So essential skill number 1. So the difference between solids, liquids, and gases and intermolecular forces. And the easiest thing is to say, let's say we're looking at, we're talking about those intermolecular forces are forces of attraction, or how close are the molecules to each other. And so solids, liquids, and gases. And the solids are much stronger than the liquids, which are much stronger than the gases. If we're going to draw a picture, if you remember right, we have these pictures that are really close together. And there's just vibrations. It's fixed in place vibrating. You guys are starting to remember the States of Matter dance, I'm sure. Old BG, Saturday Night Live, or Saturday Night Fever, sorry. Liquids, you have them, they might be kind of close together, but they also roll past other ones that are not so close together. So there's this, they move around, but see how they're still pretty close together, okay? And then finally gases, which are really far apart. And they bounce off walls, they bounce off each other, they travel in direct lines. That's basically how that's moving, okay? But solids are much stronger than liquids, are much stronger than gases. So that's the first one, that difference in strength. Then essential skill number 2 is biological molecules. So I'm just going to write bio molecules covalently bonded. Now we're not going to ask it quite so simply. What we're going to say are things like, okay, here's a list of molecules: CO2, H2O, NH3, C6H12O6, O2. And what type of bond do they all have? Well, they are all non-metals. And if you remember, non-metal plus non-metal equals covalent bond. I mean, that's basically it. You know, they're going to give you, I mean, there's going to be some other questions too, but that's primarily how it would be asked is if you have all these molecules, what is the bond type? And so you have to look at the elements in the molecule. Are they metals? Are they non-metals? And then once you determine the type of the elements in there, then you can determine the type of bond. So that's essential skill number 2. Now, essential skill number 3. Carbon is the backbone. So anytime you have carbon, it's considered organic chemistry. Organic chemistry is involving carbon. But you have carbon making all of these molecules. So we used propanol in the lab, right? That was CH3, CH2, CH2OH. What that molecule looks like is carbon, carbon, carbon. It has these H's all around it. It's like that, okay? If you have sugar, glucose, you can have it in a couple different forms. One form, though, is all these carbons. Oops. That's not a carbon. 5, 6. And what you have is an H, if I do this right, OH, H, C6H12. Oh, wait, is it double bond? Oh, I can't remember now. I'm blanking. That's not an alcohol at the edge. I think, oh, I'm totally blanking now. I want to say it's a, doesn't do very good. It doesn't do very much good if I'm having a hard time remembering. Anyways, there's oxygens. That's not right. Now you're gonna make me look it up. Here I am trying to think of something off the cuff and it's not coming out right. Okay, glucose structure, that's what I should have done. Images, there we go. I guess they are. Okay, let me share that document with you guys. Oh, bummer, where is it? Oh, okay, there we go. Okay, I'm gonna share that document. Okay. So you can see all of those are different forms of sugars, and you can see that they're rings, but all of what you don't see, everywhere you see a corner, like you see a corner here, that is a, let me make that bigger. Right there, that's a carbon. That's a C, 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 C. Those are all carbons, and there's an oxygen right there. So if you look at this one right here, 1, 2, 3, 4, 5, 6. There we go. There's more carbons. So, and their carbon is the backbone of that molecule. It is what everything else is built off of. So, carbon can form 4 bonds. It can form the most bonds. It is found to be the easiest. Now, silicon can also form 4 bonds. It's considered a metalloid, so it has a little properties of both, and it just doesn't. Now, you don't have to know the rationale of why not silicon, why carbon, but just know that carbon is the backbone for all biological molecules. So, all right. I'm sorry, and that means that the polymers, there is, on the study guide, you have to do one where you have to do the 4 macromolecules, clapin, carbohydrates, lipids, proteins, nucleic acids. And they have their monomers, S-fan, sugars, fatty acids, amino acids, and nucleic acids. That there a lot of carbon involved in those polymers. So those are some of your biological molecules, which are covalently bonded. So 2 and 3 are pretty close together. All right, let's go back for essential skill number 4, and this one is, of course, even more important since we just covered it today, and I want to make sure that you guys understand what's going on there. I'm sorry, hold on just a moment. Okay, so essential skill number 4. Okay, so that one is No, that's not. So we'll say students know how IMF. I'm going to abbreviate intermolecular force with IMF. IMF affects boiling point. Now, in order to boil, it's the same thing as vaporization, which is evaporation. I mean, they're very similar. No, not the same thing, but they're very similar. Okay, so your intermolecular forces, again, starting with the strongest, ionic, which is greater than dipole, which is greater than dispersion. And ionic is a salt, like NaCl. And those are cation plus anion, right? It's the attraction between the cation and the anion. Dipole, an example of that would be H2O, which is polar, okay? It just so happens that water is also has hydrogen bonds. And then dispersion, an example of that could be methane, CH4, which is non-polar, okay? And, or I could say, actually a better one would be the alcohol, the propanol, CH3, CH2, CH2OH. Now the OH at the end makes it a little bit polar, but the rest of this right there especially, that really makes it non-polar, okay? So you need to understand those differences in the strengths of those bonds. Now, when we put it in there, we had 3 beakers and they should have been boiling. When you have a salt with water, so let's say you have a salt where you've got water, H, and there's a partial negative here and a partial positive here. Well, then you have a Cl minus here, and there's a traction between, I'm gonna make this red, there's a traction between these two, this positive and negative, and it holds on to that water a little bit stronger. It's called an ion dipole. You don't have to know it, but that makes it pretty strong, okay? Then the dipole, right? That one is that picture we drew over and over again. I said memorize it, right? We have an oxygen covalently bonded to the hydrogens, which have the partial positives. And then that bonds to another hydrogen with its partial positive to the oxygen with its partial positive over here. And it's bonded up to another hydrogen over here, partial positive, oxygen, hydrogen. It's got a partial positive over here. Lone pairs, don't forget those lone pairs, and always bent. Not the best picture ever. You get the general idea, okay? And so that was just 3 of the molecules. You know, you can end up with 5 or whatever. So that is polar, okay? So, and I'm gonna give a little, let's do this. Let's make ionic, since I've already used red. This is ionic, okay? And then we're gonna make dipole green, okay? And that's what's happening there. So that's pretty strong. And now we're gonna make dispersion our purple, and we're gonna go on to the next page with that one. And so what you have with dispersion, if we're gonna talk about the alcohol, which we might as well, you have a carbon that has the 3, carbon with 2 hydrogens, carbon with 2 hydrogens, then you have an OH here. Well, it has this electron cloud, right? Here's the electron cloud. And let's say it pushes, I'm never gonna fit this all in, so I'm gonna take this. Let's say this would be the partial negative and this will be the partial positive. It's shifting around and it's pushing into another one. So actually this would be the bigger side, right? If I'm gonna have an accurate drawing, I'm gonna try to be accurate. Okay, and so it's another one, so that's gonna be kind of a smaller side right here, and this is the other one, C with the H, the H, the H, and this is the positive side. Okay, and then you know it goes through the rest of it. We're just going to call it R. That's the rest of that molecule. So it has this London dispersion. They're pushing into each other, creating these things. Now, it's pretty strong for dispersion because it's a liquid, okay? This is a pretty strong bond here because it's liquid, but it evaporates pretty darn fast. If we're gonna talk about other, a boiling point, I mean, think about the most common examples of non-polar molecules that are dispersion. So we've got CO2, O2, N2, CH4, right? So this is carbon dioxide, oxygen, nitrogen, all gases, methane, famous for talking about cows passing gas. These are all gases, right? To get to a gas, you have to boil. If you get liquid nitrogen, to get it to boil, it's like negative 270 or something like that degrees Celsius. So that's a really low boiling temperature, okay? Liquid oxygen, like that one is also very cold. Carbon dioxide is dry ice, and it goes straight from dry ice. It sublimates to gas, carbon dioxide gas. So these are all low boiling points. So these are absolutely, and dispersion has the lowest. Now, the highest, of course, is ionic. Like, what would it take to get salt to boil? Well, we can't even get salt to melt in our classroom. We have to take so much energy, right? So obviously, ionic is the strongest. I mean, this is just hopefully kind of leading you down that path, but that related to the lab today. Now, the other part, so that's the essential skills. So basically, I want to wrap up. That's the essential skills. Now, I still don't see any questions, and that's fine. I think it's really important to come up with some questions. I wish you guys would come up with questions, but I will just keep reviewing because that's the most important part. I hadn't had any plans for the study guide. Let me just take a look. I maybe could guess at some questions. It would be really helpful if you guys were to come up with your own questions. Oh, here we go. Sabrina, yay, Sabrina. How can you tell if a molecule is polar or non-polar? All right, so this is a fast and easy way. And actually, you know what, that's a great question. I've had a lot of students something happened to my thing. Okay, I am going to assume you're all still here. I hope it didn't mess up too bad. I'm not sure what happened, but my screen went black. Okay, I apologize if it cut off. Hopefully it didn't. I'm explaining how you know if something is polar or non-polar. Okay, so polar versus non-polar. All right. So the key to this whole thing is remembering the molecules. So I'm gonna give you guys the a shortcut. Symmetrical versus non-symmetrical. Okay. It has to be the same. Oh, good. Somebody said you're good. You're still on my screen. Okay, good. Thank you for telling me that, Sabrina. Okay, so symmetrical versus non-symmetrical. The key is this. I'm going to draw some molecules that are symmetrical, and you're going to see what I'm talking about. The most, or the easiest one, the one that's the most obvious, is methane, CH4. Okay, you're going to have to, of course, draw the Lewis structure sometimes to see this. CH4. There's 4 inches on the outside, and if I have, it's symmetrical along that line, it's symmetrical along that line. Great. Now, if I change that and I say, okay, now I have CH2F2. So I've got H's here, and then I have F's here and F's here. Actually, you know what? I'm going to make this even more difficult, actually, so that you guys can see what I'm talking about. I'm going to put an F there. Okay, so what you're going to say is, okay, let's say I cut the line right here. I'm going to say, well, it looks symmetrical that way. But if I cut the line here, okay, great, there's F's on both sides of that. F's would have to be on both sides of that. There have to be F's all the way around, or H's all the way around. It's not the same. It's not the same along both lines. And so that is not symmetrical. That is not going to work. You might think it is, but this side, right? This side and this side are not the same as this side and this side. So that's non-symmetrical. If I do CO2, C, double bond O, double bond O, okay? If we talk about this line of symmetry, it's the same on both sides. Now, you can't use, there can't be a horizontal line of symmetry because there's nothing there. Carbon isn't, in this situation, it's not bonding up and down at all. There's nothing up and down, so there's nothing to be symmetrical with that, okay? However, if I do HCN, okay, and then I draw my line of symmetry, most definitely not the same on both sides. So that's a non-symmetrical, okay? So I guess this is kind of messing you guys up. What I should have done, I'm sorry, because you're gonna get these backwards, I can feel it. Symmetrical is nonpolar, and non-symmetrical is polar. I'm starting to see a pattern there of how I was gonna mess you up. So I'm going to divide these so you know which one's which. So symmetrical, it has to be symmetrical to be nonpolar. If it's not symmetrical, then it's polar. Okay. Let's say I could also pick any of the diatomic, O double bond O, F single bond F. These are all N, triple bond N. Or I could, yeah. Or I could put those on the ends. Okay. Other non-symmetrical, anything that's bent, all bent molecules are polar. All trigonal pyramidal. I'll draw some examples of that. My favorite two I'll draw in a second. Okay. All of those are polar. Okay, so let's see. So polar, not symmetrical, and non-polar, symmetrical. Okay, so one of my favorites, water. Love water. Water's gonna be all over your tests. Just love water. Water's bent. There's an H, there's an H. You can't do the symmetry thing. If I make it like this, definitely not same side to side. Now, if I do it like this, okay, it's not exactly the same because it's sort of like it's a mirror image, but it's not the same, okay? So it's not symmetrical. NH, oops, let me do that. Okay, oops. All right, let's do my other favorite one, trigonal pyramidal, NH3. Ends up top here with the two lone pairs, H, 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 okay? Trying to do symmetry, you're like, you're clearly not symmetrical. Again, this one going down, it's like a mirror image, but it's not symmetrical. Definitely won't work, okay? I think I've done a lot of the basic symmetrical ones. I'm trying to think of something else that's kind of crazy that could be symmetrical that would be helpful to you. We covered tetrahedral where it's the same. Well, I guess I should just write that. Tetrahedral or linear has to be same all around. Okay. It has to be the same all the way around, or both sides, or however you want to look at that. But for tetrahedral, now tetrahedral linear can be polar just as easily if they're not the same all the way around. So you need to make sure that you take a look at that and look at the symmetry. Now that's a shortcut way. That's not definitive. It's not like in the rules, oh, it's all going to be just like that. But it will definitely help you if you can see if you can find that symmetry. Okay. All right. So hopefully that answers that question. Oh, there's a few more questions. How do you know, I'm going to do Mariah's. How do you know if the atoms are linear or bent? Okay. Good question. Let's take a look at that. So, linear versus bent. Okay. The bent, the way that you know is a bent has lone pairs on the central molecule. Oh, central atom, sorry, central atom. Okay. So let's do the most common two examples. Okay. The most common two would be CO2 versus H2O. Now, when you draw this, you're going to start off drawing it the same way because you just can't help yourself. There's a C double bond O because of honk. Don't forget honk. I'm just going to write that down right here. H-O-N-C, 1, 2, 3, 4. And the H is both halogens and hydrogen. So that's why the O's each get 2. And you have to finish off making sure they all get 8 by adding lone pairs. Okay. So double bond, double bond. There's only 2 atoms. There's only 2 things off the central atom. Okay. And so it's linear. You can't bend. There's nothing making them bend. They're just moving as far apart from each other as possible, and that's in a line. H2O, the temptation is to draw it like this, OH, and do the lone pairs like this. Now, that's all well and good for just a straight, just a regular Lewis dot structure, but to know the actual shape, these lone pairs are actually pushing on these H's. So in a 3-dimensional type of situation, these right here, these lone pairs are large. They have large clouds. I'm going to represent with purple because that's fun. These clouds up here, which is why it's drawn like that, they start pushing down. They start pushing down on the H's, which make it bent. So as soon as you get lone pairs on the central atom, it's going to be bent, or it could be linear. I mean, trigonal pyramidal if you only have one, like you have NH3. But that's how you would do it. And that's for H2O. The other examples are you're going to have H2S. Anything with a sulfur or an oxygen as the central atom. Anything with SO is SE. Oh yeah. SETE as central atom is going to be bent because they're going to have 2 lone pairs on the central atom, and so it's going to make it bent. All right. So that's how you would decide if it's linear or bent. Having those lone pairs. That's the quick and easy way to look at that. All right. Next one I see is, can we please go over general molecular geometry, the chart on page 1 of the notes? Yeah, we can do that. Let me see if I can pull those notes out. I don't happen to have a copy open. So let me do this really fast. Bear with me just a moment. It's opening up. Oh, that was faster than I thought it was going to be. Okay. So I'm going to share the notes with you. And I'm going to make it bigger because that is way too small for you guys, I'm sure. Okay. There we go. Look, it's color. I didn't even know it was color. Miss DeMurray made this and she pasted them in there, so. All right. So I would say this. I'm going to change this on here. It's not going to appear anywhere else but on my computer right now. We're going to say this. So you have a central atom. So one or two things on central atom. Now, if there's only one thing on the central atom, then there's only two atoms. So it's whatever. And things equal, in this case, thing equals atoms. Okay. Or for the other one, this is the tetrahedral family. See the tetrahedral family? This is the linear family. This is the tetrahedral family. 4 things on central atom, and those 4 things can be things equal to atoms or lone pairs. Okay. So, whoops, slid across. So if you look at these, the tetrahedral family, there are 4 things. So you have basically, you've got 2 structures you need to worry about. Either it's linear and it just has 1 or 2 things, or it's in the tetrahedral family and it has 4 different things on there. Those 4 things could all be atoms, and that's a straight tetrahedral shape. Of those 4 things, 3 could be atoms and 1 could be a lone pair, which in case it's trigonal pyramidal, or 2 are atoms and 2 are lone pairs, in which case it's bent. So I'm not sure if I can, I wonder if actually drawing this on the bamboo paper is going to be helpful. Let's take a look. So we could do like this. So atoms, lone pairs, shape. Okay. So if there are 4 atoms, 0 lone pairs, it's tetrahedral. Okay. If there are 3 atoms, 1 lone pair, it's trigonal pyramidal. If there's 2 atoms, 2 lone pairs, it is bent. Now, there is no such thing as 1 atom and 3 lone pairs. That is not happening, okay? So, but you'll notice that 4 plus 0 equals 4. 3 plus 1 equals 4. Oops. 2 plus 2 equals 4, okay? So these are all in that tetrahedral family. Just meaning that there are 4 things on the central atom. Okay? Now, the other option, if we do this again, atoms, lone pair, shape, if there is 1 atom attached to it, 0 lone pairs, that's linear. If there are 2 atoms, 0 lone pairs, it's linear. Okay? And so these 2 examples, this is the linear family then. Okay? So if you did this, you know, this one would be something like, okay, well, I am not going to draw like that. Let me erase that. Oh, horrible. Linear, okay. So if you had a H, it's bonded to another H. And then you could say, oh, here's the central. You can't really, but say this is central. Then this is the 1, right? That's linear. If you said CO2, oops. We're going back to CO2 because it's everywhere. C double bond O, double bond O. So C is the central atom. And then O, this oxygen is 1, this oxygen is 2. There's 2 atoms, no lone pairs on the central atom, it's linear. So really, I mean, if you just break it down and take a look at things. So let's say I'm gonna draw a couple of structures for you, and on your side of the camera, you decide what you think it's gonna be. So I'm going to make some up. I'm going to make some funky ones. PF3. I say it's funky, funky, and you may have this already on your sheet. I don't remember. Okay. SiO2. OCl2. Oops. I'm going to try to confuse you with some of these, is what I should have done. Let's do ooh. Here's one that doesn't exist at all. Okay, for the audience at home, you need to take a look at these and see if you can figure out what shape they are. Let's do PF3 first. All right. This is your central atom, P. How many things are on the central atom? Well, you would say, oh, I see 1 thing, 2 things, 3 things, 4 things, okay? And of those 4 things, 3 are atoms, 1 is a lone pair. 3 atoms, 1 lone pair, 4 things, trigonal pyramidal, okay? So this is trigonal pyramidal, all right? SiO2. Here, oops, here is your central atom. Things bond to the central atom. We have 1, 2, nothing else on there. So 2 things, both of them are just atoms. 2 things, no lone pairs, linear. Oops. All right, linear. Okay, then we look at OCl2, and O is the central atom. Okay, how many things are on that central atom? There's 1, 2, 3, 4. 2 of them are atoms, 2 are lone pairs. Oops. So go back 1, 2 atoms, 2 lone pairs, 2 atoms, 2 lone pairs, bent. Oops. So technically, I'm not drawing this how it should have been. This is what I should have done. See that? It's a horrible drawing, but hopefully you get the picture, okay? Now let's do Si2. Again, does not exist. But here's your central atom. How many things are on the central atom? 1, 2, 3, 4. 2 are atoms, 2 are lone pairs. We just did that one. It's bent. If I was going to draw it again, I would need to do an S. Coming down to I's down here. 1, 2, and then do the lone pairs on the H. All right, you got it. Hopefully that helps you, steers you in the right direction. Okay, so Reed, can we go over number 7 on the study guide? Absolutely. Let's see if I can find it now. Did I open up the study guide? Yes, there it is. Sure. Okay. Now, I say that. Oh, there it is. Okay. And it is, of course, super small, so I'm going to make it bigger. All right. The 4 biological oh, okay. So I talked a little bit about this briefly at the beginning. This is biology. It's the last page of your notes. So all you have to really know is, let's see, I'll just open up another page really quick. Oops. go. Okay. Study guide number 7. So you have 4 biological molecules, all covalently bonded, and they're polymers, and they have monomers. Clapping. Carbohydrates. You know what? Actually, I'm just going to type it right into here. I was going to start to write it. That's okay. The large molecules are polymers. The subunits are called monomers. And actually, I don't even think we had this on the test. I think we cut this out, but we decided after we already printed the notes. But I think you do have to know the clapping. Carbohydrate, because that's biology. We're expected to know that. Carbohydrates, and their unit are sugars. L, is lipids, and they're made of fatty acids. And P is for proteins, and they are made of amino acids. And the N is nucleic acids, so like DNA. And oh, am I doing this right? Nucleotides. That's right. Clapping. Carbohydrates, lipids, proteins, nucleic acids, S-band, sugars, fatty acids, amino acids, and nucleotides. So that's, again, back to biology. You guys need to be aware of that. There might be like 1 question on the test. Not an essential skill, not a big deal. You just have to know that's what those are. Then the next question for serine, what causes sickle cell anemia starting at the serine level? Okay. So serine, maybe I forgot to tell your class, you don't have to do 8 and 9. So 8 and 9, what causes sickle cell anemia and what kinds of bonds are found between base pairs. Sickle cell anemia is the blood cells end up sickle shaped, like crescent moon shaped, and they don't hold oxygen or hold it very well. And it's basically a mutation at the subunit level, at the DNA or amino acid level. Anyways, to make a long story short, you don't have to worry about it. Number 9, it's hydrogen bonds is the answer. That's what holds base pairs in DNA, but you don't have to worry about it. So 8 and 9, cross them out, you're done. All right, next question. Can you please explain when, why they are polar or non-polar? Okay, so I swear we covered this question a little while ago. Let me go back. I'm pretty sure we did. Let me share my Bamboo tablet. Yes, here we go. Okay, just to make sure I've got the question right again. Your question is, can you please explain when or why they are polar or non-polar? So the non-polar molecules, right, are symmetrical. They are symmetrical all the way around. Really what it means is there's just an equal pull, like the electronegativity is equal all the way around the central atom. And in this case, let's say CH4, it's symmetrical. There's equal electronegativity all the way around the central atom. Carbon dioxide, there's equal electronegativity on both sides. Now there's not a top or a bottom because there's nothing above and below the carbon, so you can't use that one. But it is on each side, so that's symmetrical, so it's non-polar. Oxygen, they're the same. There's equal pull electronegativity, so it's non-polar. Fluorine, like F2 and N2, equal pull. There's equal electronegativity, so that's non-polar. It's polar if the electronegativity differs going around the central atom. So, or if there's anything different. So here you've got CH2F2. The F's are different than the H's. There's different electronegativity. It's not symmetrical. It's polar. HCN, H and N are different. They have different electronegativities, different poles. It is polar. All bent molecules are polar. All trigonal pyramidal molecules are polar. And if you look, there are lone pairs on the central atom. As soon as you get lone pairs on the central atom, it is polar. So when you make that Lewis structure and you see that there are lone pairs on the central atom, you know right away it's polar, okay? For non-polar molecules, you can have tetrahedral or linear, but if you're gonna have them, they have to be the same all the way around. The electronegativities have to be the same all the way around. It's symmetrical all the way around. That's how you know it's going to be a non-polar molecule. So hopefully that helps. So I will, okay. Next question. Can we go over number 5 on the study guide? Absolutely. Let's take a look at that. There we go. Number 5. Which 4 elements make up 98% of living elements? What kind of bonds do they form? Okay. This one actually is easy. I can answer this one pretty quickly, and I'll just draw a picture because that's fun. All right. Sometimes I feel like this is my answer to everything. Okay. I started to do the number 7 on study guide here, and then I realized it was going to be just easier to do it on the study guide. Okay. So number 5, study guide. Okay. 98% are made of 4 elements. And my answer to everything, honk, H-O-N-C. Right? And what type of bond? They are all nonmetals. And if you remember, nonmetal plus nonmetal equals covalent. So the 2 answers you're looking for are H-O-N-C. And the type. So those are the 4 elements that make up. I mean, technically it's 96%, but that's fine. 98% of all living organisms. And the type of bond that they form, covalent. So that, like I said, it's pretty easy, pretty straightforward. Just got to think it through a little bit more. All right, Mariah would like to know about hydrogen bonding. That I would love to go over. Okay, so let me get my color back here. Hydrogen bonding. All right, so what I'm going to do is I'm just going to tell you essentially the way it's going to look on the test. Not essentially. As much as you need to know for the test. Let's just do that. Hydrogen bonding, okay? The important point about hydrogen bonding is that it is a stronger form of dipole bonding. Okay, that's key there. Hydrogen bonding is a stronger form of dipole bonding. And so you're going to be given some molecules probably and said, hey, what sort of bonding is occurring here? And you will not be given both dipole and hydrogen bonding unless it's like a, choose all of the above question. I can't remember. Miss DiMaria is finishing up the test and is going to have it. So I haven't seen the finished product, but you have hydrogen bonding in molecules like H2O, NH3, HF. Well, those are the key ones. And they're polar molecules, right? Here's my H2O. Here's my NH3. And we actually, on one of your worksheets, we spent some time, all 3 of these showing how they bond to each other. It was the, I want to say it was was it polarity? Oh, no, I can't remember if it was polarity. No, I think it was the Intermolecular Forces worksheet. And we spent some time showing how they were connected to each other. I drew them out for you. and how they had to be, you know, kind of offset. So like if this was the nitrogen one, like nitrogen is kind of down here with its H right here, and the bonding happens right here, right? That it's kind of offset, it's kind of close together so that they can be friendly. And so that's what hydrogen bonding is. Anytime you have dipole bonding where the hydrogen can bond to specifically, you know what I'm telling you here, nitrogen, oxygen, or fluorine. Now, this part right here is not on the test. This is something, in fact, Ms. DeMurray didn't even talk to her classes about that. I guess it's something I end up doing a lot because in AP Chem, it's really important that students know that. For you guys, not so much. Just know that hydrogen bonding happens with hydrogen bonding to a central molecule, okay? Or central atom. I say that a lot wrong. Hydrogen's bonding to a central atom. So that's where hydrogen bonding is. It's a form of dipole bonding. It's a stronger form of dipole bonding, and it's where the hydrogen bonds to a central atom, like nitrogen or oxygen or fluorine. And the molecule that we really care about, I mean, I cannot emphasize the whole water thing enough. Like, you need to be best friends with water. You need to be on a first name basis. You should be able to draw 5 water molecules like nobody's business in your sleep, knowing that it's bent, knowing that it's polar, knowing that you have dipole bonding, and that it's in fact hydrogen bonding because it's a stronger form. Knowing that the partial positives are on the hydrogen, knowing that the partial negatives on the oxygen. You need to know this. I just can't emphasize it enough. If you can do all of that, that's a good handful of points, probably a letter grade worth of points on the test, is just dealing with water and different forms of water. Anyways, please pay attention to that. All right, so that is hydrogen bonding. Okay. We still have about 5 minutes left. If you guys can think of another question, I would encourage you, there are always review questions, but I would encourage you to go to look at past units, past notes. I'm going to show you guys something. I keep bringing this up to other students, and sometimes in review sessions, and sometimes to students who come in for help. But I would strongly encourage you to type in, go to your browser, type in sciencegeek.net. Type that in. You go here. Then there's this, I'm going to make these pictures a little bit bigger. Might help. Okay, go sciencegeek.net. Then up here on the top, it says chemistry. And under chemistry, it says review. Click on the review for chemistry. Chemistry interactive review activities. So his questions are very similar to our questions. So you can go through these things. Now, let's say you've been doing it and you want to talk about it for this unit, like covalent bonding. You can do it for this unit. So if I look at covalent bonding, I like to show all the questions. Where are they? Choose the correct answer. Oh, here we go. The bond between boron and silicon is boron and silicon. Let's see. Boron is like a metalloid, but it's like a non-metal, and silicon is a metalloid, but like a non-metal. I think it's going to be covalent. And I get a happy face. Yay for me. Okay. Which of the following is a correct Lewis structure for hydrogen cyanide, HCN? We've done this a few times. Carbon is the central molecule. HONC, H-O-N-C, 1, 2, 3, 4. H has to have 1, which means that these first 2 choices are out. N, like H-O-N-C, 1, 2, 3. Nitrogen has to have 3. So A and B are out. Now D is out because nitrogen only has 1. And then carbon has to have 4. So E has 1 for hydrogen, 3 for nitrogen, and 4. You might want to pick this, but last thing you have to do, every atom but H has to have 8 electrons around it. Lines are 2, so 2 for hydrogen, great. Carbon, 2, 4, 6, 8. Carbon's done. Nitrogen, 2, 4, 6. Oh, not 8. We need a lone pair. That means that C is the correct answer. Hey. So that is one thing you can do. And for review, you can go back and let's say you have been having a really hard time with periodic trends. So you can pick one of these periodic behavior, periodic trends, and let's see. Oh, it put them in the order, smallest to largest, smallest atomic radius to largest atomic radius, lithium, cesium, potassium, sodium. And here's the other thing, this is pretty long. Like I don't want to go that long. But let's just do the first one. Lithium, cesium, potassium, sodium, rubidium. So I look at the periodic table, smallest atomic radius to largest. I know that the atomic radius decreases moving left to right and it increases moving down. So that means that the lower left-hand corner has the largest radius and the upper right-hand corner has the smallest. So I start in the lower left and it looks to me like, oh, all these elements are in the same family. So the lowest one would be cesium. Next up would be rubidium. Next up would be potassium. Next up would be sodium, and last would be lithium. And say, okay, you're like, okay, I don't want to have to do them all. So what you can do is go all the way to the bottom, and you can hit check, and it'll take it for a bit. You're like, you know what? Give me a hint because I'm not sure. The next correct letter has been added to the answer. Oh, look. From the smallest up, I did them backwards. I didn't even hit check. I did. So that means that cesium is on this side. Look, I did it all backwards. So lithium, sodium, potassium, oh, that stayed the same. Rubidium, see the hint was very helpful. And then I can say check, and good. I got them all right. See, and it fills it in for me, so I know that it's good. Okay? So lots of ways to review, because if you're running out of things to study, but I would especially coming to the final exam, that would be a fantastic thing to do. All right, so that's my big extra hint, but otherwise, I don't have anything else to talk about. We covered the essential skills. I really like that we covered Lewis dot structure, polarity, intermolecular force. We talked about hydrogen bonding. We talked about how you identify polar versus nonpolar. So I really feel like we did do a lot. Of course, I encourage you to come in and see me outside of class time. Come in before school, the break, plus lunch, after school, anytime. Come in and ask me questions. Email me questions. Whatever you can find time for, I would encourage you to do. But definitely study for this. Make it a good. This is it. I think this is an easy unit. This is a good unit to get a really good test grade in. And then the retake is not happening until after winter break. So let's do it now, and that way you don't have to worry about it. All right. Well, I will see you all in the next 2 days, maybe sooner if you guys have more questions. Otherwise, make sure that you are getting a good amount of sleep and getting something good to eat so you're ready for the test. Mariah, this helps. Oh, you're welcome, Mariah. I'm glad that I could help you guys out. This is fun for me too. All right. So then I will just, I'll see you guys later. We're signing off. Bye, guys. See you later.